Okay, so today we're going to finish up black holes. We're going to start with the Schwarzschild Radius. All right, remember there's two primary parts of the black hole. What are those two primary parts? The core, which we call the no. It's like a singularity. It's like a single point in space. Singularity. The core or the center of the black hole is the singularity, and the edge of the black hole is the event horizon. Now the Schwarzschild radius is the radius of the event horizon. So you can imagine there's a dot in space, which is the singularity, and then a sphere that goes around that dot, like a basketball. And the radius of that sphere is the Schwarzschild radius. Any guesses on what makes a black hole bigger than another black hole? The mass of the star that it came from. In fact, it is the mass of the star. The size of the Schwarzschild radius depends primarily on the, well, in fact, it depends only on the mass of the star which created the black hole. So the more massive the star that created the black hole, the more massive the black hole ends up being. It's a pretty straightforward relationship. It's not quite linear because m is under a square root if you looked at the math of it, but generally, well, in fact, the bigger the mass, the bigger the black hole. Now, do you think there's an upper limit on black holes? No. There is no upper limit on black holes. These things can be wildly massive. In fact, they think the one at the center of our galaxy is many million times the size of the sun. So many million solar masses. Carl Schwarzschild calculated this. Not that you need to know Carl, but you will need to know Schwarzschild. These are derived from Einstein's equations of general relativity. Relativity, in case you care, is broken up into two parts, special and general. Special came first, and then general came afterwards. In general, relativity deals with gravity. And so as you imagine, because we're talking about things that are really, really, really massive, gravity plays a really, really important part in it. So Carl Schwarzschild, and this was back in the 1910s, 1920s, I think, did these calculations and said, well, this is how you do it. And it's actually a fairly simple calculation. There's only 3 variables in it, and 2 of them are constants. The other one's mass. So you can figure out how big an object would be if it were a black hole using this calculation of Carl Schwarzschild. So we've known about these things, or we've theorized about these things. I can't progress this slide forward. Black holes have been theorized for about 100 years, or a little bit more than that. But they've been able to be calculated for the last 100 years. Did we watch this video last time? No? Okay. So we'll take a minute and... oh, nobody's got clickers. Time to get on it. We're going to run out of time real quick. All right, neutron degeneracy must be overcome. Electron degeneracy for neutron stars, and then neutron degeneracy for black holes. Right? Moving on. So we've kind of mentioned this already, but just in case you missed it, nothing can stop gravity once it gets beyond that neutron degeneracy. So everything just keeps collapsing and keeps getting closer and closer together and closer together until it just comes to a single point in space. That single point, that infinitely tiny space, it doesn't have any volume, but it's got tons of mass, is what we call a singularity. And because physicists don't like to deal with things that don't have any volume but have mass, we don't know what the answers to these questions are. We don't know how to deal with it. No Newtonian physics can help you at this point. In fact, Newtonian physics breaks down once you get down to the electron degeneracy phases. And so you look to quantum mechanics, but quantum mechanics can't explain what's going on inside of this singularity either. So a singularity is kind of a, not that we've given up on it, but nothing that we currently understand or know of can possibly tell us about what's happening at this point in space. And we can't study it. Why can't we study it? Why can't we look at a black hole and say, look at that singularity and how it's working? Well,
It's very small.
it's really small. It's infinitely small, so it's hard to see. You can't see something that's just a point. There are stars, but more importantly, there's an event horizon around it. And we can't get any information out of that event horizon. Information comes in the form of light. When we look at stars, we're looking at the light that's coming from them and then doing all this analysis on them. You know, is it red shifted? Is it blue shifted? What spectrum is it? You know, how hot is that particular color on a black body curve? Those types of things. But if we can't see the light coming from it, then we can't do anything with it. So that makes it very, very difficult to study this and impossible to study the singularity itself. That singularity is at the core, the center of the sphere of the black hole. And that's what we just mentioned. Nothing can help us understand this at all. And that's just a lot of ways to say that nothing we know of can help us understand it at all. Any questions about singularities that I won't be able to answer because we don't know anything about them? Okay. Yes? So what happens if we go to a black hole? Not that they will be able to go to a black hole, because the closest one is where? The center of our galaxy. And is that really close or really far away? It's so far away. It's tens of thousands of light years away from us. So we can't go to it, but what if we could go to it? Would it be helpful for us to study what's going on if we were able to go to it? And the answer is not really. Things that happen around a black hole, redshifts. You guys remember what redshifts are? It's when a wave does what? When a light source is moving away from us, right? Its frequency goes up or down? Frequency goes down. Frequency goes down, the wavelength has to go up because they're inverses of each other. And so the wavelength gets longer and longer and longer. So let's say that star was shining off in, I don't know, green color. When that star was moving away from us, it would shift a little bit. It would extend the wavelengths out. It would make these longer. And therefore, the wave would appear to us to be redshifted. And that would help us understand the velocity of the star. Well, when things are going around black holes, that gravitational shift is, yes, it could be caused by its velocity if it's moving away from us or towards us. But it's also caused by gravity itself. Gravity, and this is kind of a not so accurate way to think about it, but you can think of gravity as kind of pulling on that wave and extending it out. So when things are very close to black holes, they appear redshifted. So let's suppose that you had a flashlight and it was pointing towards you and it was a blue flashlight. And you threw it towards the black hole such that it was shining towards you all the time. Well, that light would eventually shift from blue down through green, down to yellow, and down to red until it reached the black hole's event horizon, in which case it would just go away completely. So at the near black holes, you see these gravitational redshifts. Time dilations. This is kind of a weirdo thing to think about, but this is kind of a relativity thing. Einstein suggested that in intense gravitational fields, or in intense gravitational fields, time appears to slow down for an observer watching something in that field. And that is true as well. So if you were watching somebody, or if you were looking at somebody that was close to a black hole, and they had this gigantic stopwatch that you could look at, the time that you see on their stopwatch would appear to run more slowly than yours. So let's say that you were orbiting a black hole and you were significantly far away. and you synchronized your watch with somebody else's, and you sent them closer to the black hole. So 1 second for you would click off. I don't know how close I am to 1 second, but something like that. Now, as you're watching them, their clock would appear to go. So every one of your seconds, or sorry, every one of their seconds would be 2 of yours. So their clock is running, say, half as slow, or half as fast, rather. And the closer you get to that gravitational force, the center of the gravitational field, the slower that their time would appear to go. And you can extend this out really long times. The calculation for that is much more complicated than the Schwarzschild radius, so we're not going to talk about it. But yeah, Wes. They would look at you. Well, for them, it would appear regular. So for them, they look at their stopwatch and be like, oh, time's clicking like it normally does. But when they looked at your clock would be going really fast. So what happens there, and if you've ever seen the movie Interstellar, they did a fairly good job with it. One of those guys went closer, I guess 3 of them went close to the black hole, and their time slowed down with respect to the guy in the station that was orbiting. So he aged, 40 years? Well, they went down and aged maybe 24 hours. It can be that significant of an effect depending on how close you are to the black hole. It's relative to you as a person, though. If you were going to a black hole, you wouldn't notice anything different. You'd be like, okay, my time, my clock, my stuff is going fine. But if you were looking at somebody else in relation to that black hole, their clock would be moving differently. If they were closer to it, then their time would be moving slower, what you think was slower. Because, and this is where it really becomes difficult to follow, that space and time are one entity. It's not that here's some space and then time progresses differently than space. They're all together. So we talked the other day about how black holes cause that warp in space, how they bend space. They're also bending time as well. Because, yeah, it's really radical stuff. And the calculations are just painful. But this happens, and we've proven this happens. How can we do this? Because we can't get to a black hole. That's fine. What we've done is we've taken atomic clocks, the clocks that are accurate within a millionth or a billionth of a second. We've synchronized them on Earth, and then we sent one into orbit and spun it around for a while in orbit. Well, even though they didn't get very far away from Earth, let's say gravity on the Earth is 9.8, and they went up to orbit and their gravity was, say, 9.6. If you spend enough time out there, your clocks eventually get out of sync. And so it's true. When you spend some time in orbit, where the gravity is not so big as it is on the Earth, your clock would run slower. Now, it's nothing significant. Astronauts would go up there, and if they spend a year up there, maybe they come back and they're half a second younger than the person that stayed on space. It's nothing. But that's only because the Earth's gravity is so small. If you got next to something as large as a black hole, maybe many million solar masses, then that gravitational effect would be much, much larger. And so these actually have proven what Einstein came up with 120 years ago, 1910 or something like that, whenever he came up with general relativity. That was special relativity. Well, no, that was general. Sorry. Two get confusing. So that's the other thing that would happen near black holes. The third thing that we're going to mention, and there's some other things that happen, but the third primary thing, and some of you have heard about this, is a process known as spaghettification. Tidal forces, like the forces that the Earth and the Moon exert on each other, contract and expand. And this is, we talked about Europa, and how Europa can have a liquid core underneath its icy top with the fish in it. How can it have a liquid core if it's underneath the surface? Well, it's because Jupiter is expanding and contracting Europa while it's going around in orbit. Those are called tidal forces. It's the difference in gravity between one side of the planet and the other, basically. It's very, very small, but over time it occurs. The difference, if you are close to the black hole, the difference between the gravity on your feet and on your head would result in you stretching out, or anything stretching out, really. And thus spaghettifying if you were able to be spaghettified. So your feet get pulled, and so does your head, but it doesn't get pulled quite as fast as your feet does, and so your feet accelerate towards, and you get stretched out like a piece of spaghetti. Or get ripped in half. Yeah. These tidal forces are the same reason why Saturn has rings. It should have a large moon there, but what happened is that the tidal forces on the moon extended it, and it broke apart and formed rings instead of moons. And this happens all the time with objects around black holes. You don't tend to find objects orbiting really, really close to the event horizon because the tidal forces there are so strong. It just breaks them apart. So gravity is significant to this, and mass is significant to gravity, so it all kind of plays together. Plays together nicely. All right, so how exactly does a black hole form? Well, a black hole is going to form exactly like every other star that we've talked about. It's going to start with a molecular cloud. It's going to go from the molecular cloud to what? A protostar. From the protostar to a fusion star, main sequence star, upper left, because it has to be very, very massive. It has to be a supermassive star. It's going to go to red giant phase. It probably has a horizontal branch where it's forming these other things. And eventually it's supernovas. Now, if that supernova, if the star's massive enough, that supernova won't get rid of enough stuff. If it doesn't have the mass of supernova, just as a review, if it's less than 1.4 solar masses, it won't supernova. Rather, it will planetary nebula, form a planetary nebula around it. What's left over is the white dwarf. And electron degeneracy stops that white dwarf from collapsing. If the thing's more massive, it will supernova, and it will pass by the white dwarf phase because it's too massive to stop at electron degeneracy, and it will come down to neutron degeneracy. So that's the stars of 2 or 3 solar masses. Now, if it gets much larger than that, somewhere between 3 and 4 solar masses and above, anything above that, it will progress past the neutron degeneracy phase and create a black hole. So black hole formation is nothing all that special. If a star has more mass left behind after the supernova than 3 or 4 solar masses, it's going to become a black hole. The progression of star formation, the progression of black hole formation is exactly the same as it is for every other star. Can anybody think of a situation where a black hole could form not like this? How else might a black hole form? Okay, white dwarfs won't do it because they're already too small, but maybe a neutron star. If a neutron star had a companion star, a binary star, it could eventually retain enough mass to collapse into a black hole as well. So if a star did not start with that much mass to begin with, but gain that much mass, now it would have to be pretty close to the boundary. Stars, when they're companion stars, don't pick up all that much mass. So it has to be pretty close to it. As we watched in the video, how exactly we find them? We look for gravity. We look for the gravity of a black hole. And this is a simulation from UCLA Galactic Center. And it shows the progression of stars around a potential black hole over the course of 20 or 30 years. Now, see how they orbit. They orbit just like planets would orbit the sun, except, of course, they're stars. And so they're orbiting the galactic center. Now, they also have gravitational attraction to each other, and so you see some funny things going on at the beginning and the end, because they are supermassive things. They're going to have gravitational attraction to each other. But overall, they all appear to be orbiting this central location here where we believe that there's a black hole. So if we see something that has a gravitational effect on other things, but we can't see what that thing is, it's likely a black hole. And because we know mathematics from Kepler and all these other early orbital scientists, we can figure out the mass of these things. Anything that's orbiting something else, it's actually relatively simple to find the mass of. We can find the mass of the star based on the orbits of our planets. We can find the mass of this black hole based on the orbits of these stars. And as we mentioned, we can calculate a mass of the center of our solar system to be about a couple million solar masses big. That's a big old black hole. Just a reminder about accretion disks. In which of these situations would an accretion disk form? They exist. Yeah. In fact, they collapse and crash into each other. That's how recently we discovered gravitational waves. Yeah. Well, they hit each other. They absorb each other.
How does that work if you have two core or two little?
Let's make one bigger one. Yeah, we've got to have a binary system where one can steal matter from the other. White dwarf binaries can't do it because they don't have mass they can exchange. They're already pretty small. Lone stars can't do it on their own. Black hole binaries, again, they don't have mass to exchange. They can't take mass from one black hole and give it to the other. That mass is pretty gravitationally attracted to itself. So another way that we calculate, or another way that we can find black holes is by accretion disks. Sometimes those black holes will get close to other stars and accrete matter from them. So just like the white dwarf red giant binaries, or the neutron star red giant binaries, or any giant star binary with a gravitationally smaller star, it would suck material off the outside of that star. So if a black hole and a red giant or another giant star were in a binary system together, that black hole would suck material off the larger star. What happens to that material when it gets sucked off the larger star? It's spinning around, and eventually it falls into the black hole. Now that matter, once it gets going around and around and around, heats up, and it heats up so much that it emits in the X-ray part of the spectrum. So what we can do is we can look for what we call X-ray binaries. A binary star system, or a binary system, a star going around something else that's emitting binary rays, or not binary rays, that's emitting X-rays. So if we see an X-ray binary, that's something to study, because normal binaries would just cut off visible light or maybe UV radiation. But an X-ray binary or a black hole binary system would emit these X-rays in large amounts. And we think we've found several of these things, which are black hole candidates. So those are at least two of the primary ways to find them. We look for gravitational attraction, and then look for what we call X-ray binaries. If we find either one of those, it's pretty good evidence that there's a black hole in existence in that particular spot.